As an oil well is drilled, each new section of drill pipe supports its own weight and that of the pipe and the drill bit beneath it. Calculate the stretch in a new 6.00 meter length of a steel pipe that supports a 3.00 kilometer pipe having a mass of 20.0 kilogram per meter and a 100 kilogram drill bit. The pipe is equivalent in strength to a solid cylinder 5.00 centimeter in diameter. So what are we given here? We are given the newly added pipe. Let's represent it by L naught. That's 6.00 meters. And we also know the length of the pipes beneath it. They are up to 3,000 meters or 3.00 kilometers. That's equal to 3,000 meters. We also know the length density, that's to mean mass per unit length. So the pipes have a mass of 20.0 kilogram per meter. So if you multiply the length by this density, we get the mass of each one. So 20.0 kilograms per meter. And there is a drill bit. Let's represent it by mass of drill bit, dB, 100 kilograms. And it says steel pipe, and that means because it's going to be tensile strength and stress, we have a table value, which is a Young's modulus, and that's equal to 2.1 times 10 to the 11 Newton per meter squared. And you also know that these pipes are steel pipes and they are like cylinder. Therefore, we know that the diameter is 5 centimeters. And that means the radius is going to be half of the diameter, 1/2 of 1/2 of 5 centimeters. That's equal to 2.50 centimeter, but we need it in meters, therefore we convert this to meters, and that's equal to 0.0250 meter. Alright, so now what we are asked to find is the stretch, that's the length or change in length of the newly added pipe. Now to clarify the question, let's sketch it. So we have an oil well drilled to a depth of 3,000 meters. So let's draw the last pipe. The deepest pipe is a pipe which was actually inserted initially, and it's connected to a drill bit. Drill bit is the one which actually drills, and let's connect this let's call it drill bit. Now there are a number of pipes inserted already. They are up to 3,000 meters, means if each one is 6, there are actually 500 of them already inserted. Alright, so now this is the last one of the 3,000 meters, but now we have another one which is inserted, the newly inserted one, the newly drilled pipe. it has a length of L naught. And the pipes beneath this newly added pipes are up to 3000 meters. Let's represent that by LB. So now we have 3000 plus 6 meters drilled into that oil well with a drill bit at the end. So how do we find the force exerted by these masses, by these pipes? To do that, we need to find the total mass first. So what is the total mass? The total mass is going to be mass of the newly added pipe plus mass of the pipes beneath this newly added, let's call it MB, plus mass of the drill bit. Alright, so mass of the pipes is not directly given, but we are told their length, and we are also told that every meter of these pipes has a mass of 20.0 kilogram. Therefore, total mass is going to be the length of the newly added pipe plus the length of the pipes beneath multiplied by the length density, which is mass per unit length, plus mass of the drill bit. Alright, so the total mass is going to be equal to L naught is known, 6.00 meters, and the mass of all the pipes beneath this newly added pipe is 3000 meters. If you multiply this by the length density, which is 20.0 kilogram, divided by the length meter, plus the mass of the drill bit, which is given to be 100 kilograms, this will be the total mass. And this is equal to 60,220 kilograms. Alright, so what is the force going to be? The force is actually equal to the weight of everything that we have in that well times the gravitational acceleration. Oh, sorry. Alright, that's going to be total mass times gravitational acceleration. And the total mass we calculated earlier is 60,220 kilograms. Multiply that by gravitational acceleration. That yields 590,000. $156 newtons. So now we know the force. Now we have everything we need to calculate for delta L. To do that, we use the stress is equal to Young's modulus multiplied by the strain. Force per unit area is the stress, and that is equal to Young's modulus multiplied by the strain, and the strain is delta L over L naught. So we are required to find the stretch, which is delta L, so we can rearrange the equation such that delta L will be on one side, everything else on the other side. FL naught, multiplying both sides by L naught, and dividing both sides by Y. That yields YA. Now let's plug in the numbers. Alright, before we do that, let's deal with area also. So FL naught divided by Y multiplied by R squared. Remember, this is like a solid cylinder. Therefore, the area perpendicular to the force exerted is a circle. So that's pi r squared. Plug in the numbers. F we have calculated earlier is 590,156 newtons. The original length of the newly added pipe is 6 meters. Divide the whole thing by Y, which is table value 2.1 times 10 to the 11 Newton per meter squared, multiplied by pi, multiplied by the radius squared, which is 0.0250 meters squared. And that's equal to 8.59 times 10 to the power of -3 meters. And this is approximately equal to 9 millimeters. So the newly added pipe will stretch by 9 millimeters.